Welcome to PanGlobal's Correction Series, which features typical calculation problems and their suggested solutions from our subject matter experts. In this video, we will work step by step through a problem that our technical staff have devised to help you apply the knowledge and concepts gained from your PanGlobal learning materials. This week, we are looking at an example for calculating angular acceleration. Defining the problem. A turbine is started up from rest to a final speed of 3,600 RPM in 20 minutes. What was the angular acceleration of the turbine shaft in radians per second squared? Pause the video now to work through on your own, or keep watching for the step-by-step solution. Equation used. Total angular acceleration in radians per second squared, represented by alpha, equals the change in angular velocity, delta omega measured in radians per second, over the change in time, delta t in seconds. Expanded, this equals the final angular velocity, omega 2, minus the initial angular velocity, omega 1, over the final time, t2, minus the initial time, t1. So, what are the known elements from the problem statement? We can list them here. The starting or rest RPM is equal to 0. The final speed is 3,600 RPM, and the time to achieve the maximum speed is 20 minutes. It is critical that turbine shafts accelerate smoothly, so we will assume that there is a constant acceleration. The unknown element is the rate of acceleration. Remember that total angular acceleration in radians per second squared, represented by alpha, equals the change in angular velocity, delta omega measured in radians per second, over the change in time, delta t in seconds. The equation does not require adjusting, as it already isolates the angular acceleration, alpha. We will be working with the expanded equation. Total angular acceleration, alpha, equals the final angular velocity, omega 2, minus the initial angular velocity, omega 1, over the final time, t2, minus the initial time, t1. Inserting known elements. Final angular velocity, omega 2, equals 3,600 RPM and must be converted to radians per second squared. Initial angular velocity, omega 1, equals 0 radians per second. Final time, t2, equals 20 minutes and must be converted into seconds. Initial time, t1, equals 0 seconds. Total angular acceleration, alpha, is our unknown. To calculate angular acceleration, we need to convert several of the known elements to reflect the common units. First, the time needs to be converted to reflect its measure in seconds. To convert minutes to seconds, we need to multiply the number of minutes by 60. Thus, 20 minutes times 60 seconds per minute equals 1,200 seconds. Second, the angular velocity needs to be converted from revolutions per minute into radians per second. The symbol for radians per second is the lowercase Greek letter omega, which looks like a W. To convert RPM to radians per second, we use the following formula. 2 times pi times n over 60, where n is the speed in RPM. The rest RPM is 0, so omega 1 is equal to 0. The final RPM is 3,600, which, when entered into the formula as 2 times pi times 3,600 over 60, which comes to 376.99. Therefore, omega 2 is equal to 376.99 radians per second. The known elements are now in place for the calculation. Angular acceleration, identified by the lowercase Greek letter alpha, is measured in radians per second squared and is equal to the change in angular velocity divided by time in seconds. In other words, if we subtract the initial velocity from the final velocity and then divide it by the time it took to get from one velocity to the other, we will obtain the angular acceleration of the rotating shaft. Using the formula for total angular acceleration and substituting for our known values, we see total angular acceleration is equal to 376.99 radians per second minus 0 radians per second over 1,200 seconds. Solving the formula provides us with the value 0.314. The total angular acceleration experienced by the turbine is 0.314 radians per second squared.